Thank you. So first, I would like to thank Zhicheng for the very kind introduction and the invitation. And it's a great pleasure to have the opportunity to give a seminar talk at Nanyang Technological University. So today, as you can see, the title is the Optimal Relative Performance in Mean-field Contribution Games. So this is related to the design of some criteria, performance criteria, or in some literature, it's also called a sharing rule or allocation rule. And to be honest, I'm also a learner in this area, the design of some criteria. So if you have any comments, suggestions, or even criticisms, feel free to let me know. So now let's start. So the idea, I think the basic idea behind this research is very simple, and let's just look at an example. Say let's consider an n-player game. Assume it's symmetric. Now each player will choose some effort level. So we use A to represent effort level. So A is in general is positive. So once choose effort level A, then the player will pay the effort cost. So which is C. Then the team's reward, the total reward for the team is given by this function here. In particular, here inside it, the reward depends on the aggregate or the average performance of these players. And for scaling issue, let me just multiply by n here. Now suppose, so this is a total reward. Now suppose this reward is distributed evenly among all the players. Then the payoff for each player is represented by this expression here. In particular, this is the average reward for each player, right? And this is the cost for the representative player. Of course, in general, naturally, we assume these are increasing functions, R and C are increasing functions. So here is the trade-off from this payoff function. We can see that there's a trade-off. On the one hand, the player would like to make more effort so that this average performance will be increased. On the other hand, he's faced this dilemma that if he make too much effort, then he will incur a lot of cost for the effort. So there's a trade-off between cooperation. I call this is a kind of cooperation, and the selfishness. This is selfishness. And so such kind of game, it's essentially it's like a public goods game or a variation of public goods game. And often such kind of game has this free ride issue. Let's just do some computation. So let's assume R here is square root of x. C here is just x squared. Then we can compute. So each player try to maximize his n payoff. So the payoff function is I copied here. And then we can compute, and there is a unique Nash equilibrium, which is given here. And then this, of course, this is equilibrium control. And then under this control, the player's payoff is given by this v hat, which has this expression. Then from these two, a hat and v hat, we can see that if as n goes to infinity, as the number of players goes to infinity, a hat goes to 0 and v hat goes to 0. And pay attention. Remember that here we don't have any scaling issue. Because here we just take the average, so no scaling issue. But even without the scaling issue, we can see that these two goes to 0, which means there's the free ride issue increase as the number of players increase. Then we can just compare the centralized control, compare this decentralized control. So when we talk about Nash equilibrium, we mean this, we also call it decentralized control. When we talk about the centralized control, so here, the centralized control means that each player completely cooperate with each other, and each player only care about the team's total reward, and the player doesn't care about his own cost or his own benefit. So this, in this case, I call it a centralized control. So for this is a centralized control, right? The player try to maximize the total reward, and then of course minus the total cost. Each player completely cooperate, so the supremacy is over all AI. Of course, equivalently, if we look at the average, equivalently I just divided by n, and then I look at the average payoff. So this is average payoff. Then we can just easily solve this optimization problem. So optimal value is given by v hat here, v star, and it is of course this is like more it's like coincidence here. It's independent of n, and the a star is independent of n. So the key point is that we can see that this v star is and the a star is larger than this a hat and b hat, right? So which means my point is in the original game, right? The equilibrium is very inefficient, especially when n is large and there is a severe free rider issue. Of course, this lies in the fact that the reward is distributed evenly regardless of the contribution of each player. But then we would like to fix this issue, right? And then a very natural idea, which is basically from daily life experience, right? The natural idea is to fix this issue is that we give more reward for those players who perform better. This is a very natural idea. So basically, here we can just introduce some relative performance criteria, and we distributed the reward based on this relative performance criteria. Now, for example, we can redistribute the reward like this. In particular, this is the original reward. This term original reward, and this term, of course, is a cost for each player I cost. And then I redistributed the reward according to this criteria. So this is a fixed amount. So this is a fixed ratio, fixed proportion, which means no matter what your performance is, you can guarantee to receive 1 minus beta that match proportion. But now for this proportion, it depends on the relative performance. So this is like my performance, and this is like the average performance. Right. So if I increase my performance, and then this ratio is increased, then I get a larger share. And then say each player. So now each player's payoff function is given by this expression here, and each player try to maximize this payoff function. Now we can compute and find the Nash equilibrium. So this is a unique Nash equilibrium. And this is the associated payoff. And we can see that, in particular, we can see that as n goes to infinity, right? This no longer goes to 0, and this no longer goes to 0. And it's easy to see that a beta here would be greater than a hat, and v beta greater than v hat, where a hat, b hat is the original game, is in the original game. Now, in particular, right? In particular, if I choose beta, right? If I carefully choose beta, if I choose beta to be half, then from this expression I can show that v beta will be equal to v star. V star is the value in the centralized control. So this is the best optimal value. This is the best one. So if I carefully choose beta, my value in this game can attain the maximum, the best one. And of course, and then my equilibrium control will be the same as the centralized control. In other words, this beta, when beta is equal to half, this beta produces an equilibrium which achieves the maximum possible value. And we call such a relative performance criteria an optimal one. So let me emphasize again, an optimal relative performance criteria provides a mechanism to implement the optimal centralized solution in a decentralized game. So optimal centralized solution is, as I mentioned, is a case where players completely cooperate and only cares about the team's benefit. Right? And decentralized in decentralized game, players only cares about his own benefit. So in this talk, of course, in this talk, the goal in this talk is to study optimal relative performance criteria for mean field contribution games. So basically, roughly speaking, the structure or the model is very similar to the example I presented. But of course, it is more general in the sense that it can be dynamic. And then also there are a lot of relative performance criteria, infinite many relative performance criteria, and we will mainly consider 3 types of relative performance criteria. And then we will first look at one team. We will first look at one team, and within this team there are a continuum of players. So we will look at the intra-team games, and then later, after that, we will look at a 2-layer game. So we will have an infinite a continuum of teams, and each team will have a continuum of team members. So it's a 2-layer game. Of course, the reason we work in mean field setup is for trackability or for simplicity, to be honest. If it is an n-player game, the solution it might still be possible to get a solution, but the solution looks ugly, to be honest. So, of course, this, as I mentioned, this is related to mechanism design or design the performance criteria. So this is in mathematical economics, this is called a mechanism design, or this is related to implementation theory. And so this is like a huge area in economics, and I'm not gonna go to the literature review in this big area. But instead, I'm gonna mention some literature which is related to mechanism design in mean field games. So with a mean field setup, in particular, here is a incomplete list. So here, I guess probably almost all of us know this. Like this is a tale of principal and many agents, right? So this study principal agent problem, where the principal try to design a best contract, right? Design a best contract. Similarly, so these 3 papers, these papers also study principal agent problems, one principal and many agents. And so the difference is that here in this paper, they consider, I would say, consider general setup, and these papers, so these 3 or 4 papers, they consider more particular models, and their solution, because the model is more specific, they have like a nice explicit solution for these 3. Of course, this also has some explicit solution, but the theory is more general. And also, as I mentioned, this talk involves, I will talk about the 2-layer mean field game. So let me also mention some literature related to 2-layer games involving mean field setup. In particular, so I list these 3. I believe there should be some more, but there's not too much literature on this. In particular, 2-layer games, 2-layer mean field games. So these first 2, indeed they are 2-layer games, but they're on the top layer. They have, it's like this. Roughly speaking, it's like this. They have a finitely many teams, and within each team there are infinitely many players. So it's like it is 2-layer game, but the top layer is n-player game, and the bottom layer is a mean field game. And so for this one, for this paper, we have so for this paper, it is indeed a 2-layer mean field game, a mean field game of a mean field game. But it's quite different from this talk, from work in this talk. The difference first, of course, the model is different, the problem is different. Second, in terms of formulation, I would say in terms of in terms of the the problem itself, this paper, right? This paper, indeed, it also relates to relative performance criteria, but that relative performance criteria in this paper, it's given exogenous. It's not a part of a control. But in this talk, our relative performance criteria is part of the control, right? And in the relative performance criteria in this paper, of course, in this paper is not optimal. And here in our work, in this talk, we aim to find the optimal one. And another difference is that in this paper, we consider two-layer games. I mean, in this paper, they consider two-layer games, but so two-layer equilibrium. The equilibrium is constructed from the bottom layer and then to top layer. And in today's talk, the equilibrium will be constructed. Two-layer equilibrium will be constructed from the top layer, then down to bottom layer. And of course, our contribution of the work in today's talk is that first, as I mentioned, this is like a Nash implementation lies in Nash implementation. Nash implementation is that we design some mechanism so that the centralized solution can be realized in a decentralized game. So this is called the Nash implementation. So in most of the literature, I found that in most of the literature, they only consider static game. So I think that one contribution of our work is that we can also consider in a dynamic and stochastic models. This is one contribution. Another contribution is that we consider this mechanism design with the presence of team-wise competition. Of course, this is also related to the formulation and solution of a two-layer mean-field game, which is the other contribution. So, any questions so far? So, if no question, let's first. I probably need to speed up a little bit. First, let's first consider a static model. So one period model, simple model. Consider we have one team, a continuum of homogeneous players. By the way, in this talk, I will mainly focus on a homogeneous case. Probably only until the end. If there are some time left, I will consider talk about the inhomogeneous case. But here, let's mainly focus on homogeneous case. So take a representative player I, and the player I choose some effort level A, and pay the cost C. Assume this cost function C is nice enough. For example, convex increasing, and then we assume player I's performance is random. So the realized performance is given by this function phi here. So A here is input, so it's effort level, and then there's some individual noise xi. So then of course this means that the effort level, the effort input is not observable by other players. Only the realized performance can be observed. I assume this holds. So this means that if my effort level is A, then on average my performance is A. But I think this assumption is without a loss of generality, because otherwise you can just rescale the cost function. You just rescale the cost function so that this holds. So this is just without a loss of generality. And then, of course, by a law of large numbers, the team's aggregate performance is given by this A bar here. We just do the integral. Yeah. And then team's aggregate reward is represented by this function R. let's first look at the centralized optimal control problem. In the centralized optimal control problem, each team member completely cooperates and works for the benefit of the whole team, right? So this is a target function, the reward minus the total cost. Of course, each player will choose AI, and then by each player, of course, we allow each player to choose different A. We choose different A. But because by the convexity of C here, we can show that this superman, in particular this superman, will be the same as this superman. Here, the difference is here each player chooses a different one, and here all the players choose the same one. It's a difference, but you can easily show this is equal. And then we assume there exists the optimal solution. So the superman, this superman is attained. Now, let's look at the decentralized problem. And for decentralized problem, let's first introduce the relative performance criteria. So this is a criteria to redistribute the reward. So we say F is a relative performance criteria if it satisfies these two conditions. First, it is increasing. Okay, first let me introduce. So first, it is F is a function of two variables. The first argument X here, it represents it represents players realized performance. So this X represents the performance. B represents the distribution of all the players' performance. Then here, this means F is increasing in X, which means the better performance implies more shares. And then also we have this condition. By the way, the FD is just the CDF of the distribution D. So this condition it means that the total reward is balanced after redistribution. Let's look at some typical examples. The first one is, I call it a ratio-based relative performance criteria. So it is based on this ratio, which is the same as the one in the motivating example. In particular here, of course, in particular, this MD is just the average of the distribution, the mean of the distribution D. And beta here captures the competition intensity between players. Second one is, I call it a ratio-based one, because the different-based one, because this is just the difference between my performance and the average performance. So I call it the difference-based one. Third one is called a rank-based one. So it's like this. Here, first we have I call it a rank function R. It is increasing. So it means that the better the rank is, the better share you will get. So say, for example, if you are, if I'm in the bottom 10%, right? If I'm in the bottom 10%, then my reward or my share will be R 0.1. Of course, this condition is the balance condition, so that the total reward is balanced after distribution. And then the relative performance criteria, this function is defined in terms of this rank function. In particular, this is your rank, right? You input your rank. This is a rank, and based on your rank, you get your share. And you can see we have these two cases. The second case here is that if there's a tie, right? If there's a tie, if you and I both rank first, then we share the reward evenly. So this is the case when there is a tie. And so let's again we consider some matrices. So suppose take a representative player, and the representative player use control AI, and all the other players use control A. Then this would be the expected payoff for the representative player. So again, this is original reward, and this is the cost for player I. And then this is a redistribution. This is a redistribution based on the relative performance criteria. In particular, this is a performance. This is the performance of the representative player. And this is a distribution of the performance of all the players, right? Because this is random, right? Because this is random, so this we take the expectation. And then, of course, we can. So suppose f is given. Suppose f is given. We say A is equilibrium if this holds. So this is essentially a Nash equilibrium, right? Given all the other player use strategy A hat, the best strategy for me is also A hat. So this is a Nash equilibrium. Of course, this Nash equilibrium A hat may depend on F, right? For different F, A hat may be different, right? Now, we say F is an optimal relative performance criteria if there exists an equilibrium A hat with respect to this F, so that under this equilibrium, the value for each player, right? The value for each player is the same as the value for the centralized problem, for centralized control. So this is what we call optimal.
Hi, Dr. Zhou. May I
Yep.
ask one quick question about
Sure.
the RA in the first equation? So, do you actually assume that when we distribute the reward calculation, the payer can observe the A? So my question is why inside the R is not defined AX, is A instead here?
Can you repeat your question?
I mean, the first equation, the payer I's expected payoff, you use RA, but I wonder why is not R of phi of A.
Oh, you mean here? Oh, because here we are in because here we are in the mean field setup. In the mean field setup, once it average out, it becomes deterministic. If we look at right, so let's see. So this is a random, right? The realized performance, this is random, but because we have because we are in the mean field setup, so if we take by law of large numbers, right? By law of large numbers, the realized the overall performance, right? The overall performance by law of large numbers, this will converge to the average, to the expectation of this one, right? So consider n player game, right? This will converge to the will converge with probability 1 to the average of this, and the average of this, and because of this condition, it is exactly A.
I see. Okay, so that was actually inside the expectation, but by law of large number, you take it out.
Yes,
like that.
Yes.
Okay.
By law of large number, and this is essentially the one important reason why I work in mean field setup, because it is deterministic. In some sense, it is deterministic. Yeah.
I see. Thank you.
Yeah. So here, as I mentioned, so this definition of optimal relative performance criteria, and let me emphasize again, relative performance criteria is such that if it is implemented for reward redistribution, right, then each player will get the best possible payoff as if the control is centralized. And so let's recall by assumption, right? By assumption, we assume A star there. By assumption, A star is the global optimizer for this function, which this is the payoff for the centralized control, right? I assume there is a global maximum point. So here is one result which says if I define beta like this, right? If I define my beta like this, then this then I define a relative performance ratio-based relative performance criteria with beta defined like this, then it is an optimal relative performance criteria. Moreover, if R is straight concave, then this A star is in fact is unique equilibrium with respect to this F. Of course, one first intuition is that if beta should be carefully chosen, right? If beta is too small, right? If beta is too small, then there will be too much free ride effect. And if beta is too large, then there will be too much competition, which is also not good. So this is one kind of explanation why beta and why we have to have to be carefully chosen. And then the proof for this result is straightforward. Once you know what the beta is, right? first of all, you can write out the payoff function, right? Suppose my f is given like this. Suppose other player use a star and I use a, right? Then this would be the reward function for me. Then recall that, pay attention that this is linear in A and this is convex in A. So the whole thing is concave. Then I take the derivative. And the derivative, of course, is given by this. And then because beta is like this, then I can rewrite it like this. And then because A star is the global maximum, right? A star is global maximum, then is the derivative is equal to 0. Derivative is equal to 0. Of course, here I assume A star is positive. For example, A star is positive, then it is 0. And we have a critical point for a concave function, so it is the global maximum. So this shows A star is the equilibrium. Of course, as for uniqueness, it requires some extra work, but still, it's not difficult. And this idea, in fact, also works for dynamic case, although the dynamic case is more complicated. But the essential idea is here. It lies in this proof. So this this is for optimal ratio based one, right? We also have an optimal rank based one. If gamma is defined like this, right, and then this difference based relative performance is optimal if gamma is defined like this. And moreover, under some other assumption, some monotonicity assumption, the equilibrium is unique. And then we also have a result for rank based one. So remember, for the rank based relative performance criteria, it involves some rank function R, right? Involves the rank function R. So here we have the result. So this result, in fact, is induced from the previous two. For the first result, right? Now I have this, I define the rank function R like this. In particular, this beta, right? In particular, this beta is from the optimal ratio based relative performance criteria. So if we use the beta from the previous result and define R like this, and then this F of course defined through this R, right? Then this F is the optimal relative performance criteria. In particular, this F inverse, this is a quantile function. So F inverse is a quantile function of the distribution of this random variable phi AX. So this result is induced. So this result is induced from the optimal ratio-based one. Similarly, we have the result which is induced by the optimal difference-based one. Let me check the time. Okay, time flies. So let me comment that the proof of this previous result does not rely on particular distribution of this phi here. So with some knowledge, with the knowledge of this distribution, we can construct a more rank-based one. So for example, if I assume phi takes this form AX, where X is uniform distribution from 0 to 2, and I can show that as long as R is increasing continuous concave, of course, this condition, and as long as R1 is equal to this, then F is the rank-based performance criteria F would be an optimal optimal one. Of course, there will be infinitely many R satisfy these conditions. So this is one period model. Let's look at the multi-period model in discrete time. So for multi-period model in discrete time, the result can be generalized to continuous time. So let's look at the setup. Again, a continuum of players. So we have this time we have so we have individual noise xi. Of course, I assume they are ID. I also assume x1, x2, etc. They are independent. So which means independent in time. And we assume we have a common noise y. So of course, y is independent of x. And for each player, right? Each player will so each player's control is given by this sequence A0 up to AN minus 1. In general, right? Each player's control will depend on his individual noise as well as the common noise. So I define the set of these control as A and tilde. But sometimes we will also consider the control which only depend on the common noise, And for these control, I define the set A. So A tilde is larger set. A tilde here is a larger set. Now, player I's performance from period K to period K plus 1 is defined as is given by this function phi k. Again, it is stochastic, right? As you can see, stochastic is like the one static model here. It's the same as a static model, and I make the same assumption. And of course, here I assume phi only depend on the individual noise instead of rather than common noise. In terms of modeling, this is fine because phi here anyway. Because phi here I want to capture the individual performance, right? Individual performance, and for individual performance, of course, if we only consider individual noise, that's fine. And also for common noise, right? For common noise, I will incorporate into this R here anyway, because the common noise. We can just shift the effect of common noise from this phi to this R. In terms of modeling, that's fine. Of course, then we have aggregate performance, aggregate cumulative performance of the team. Right? This is you just sum the performance together for each period. And in particular, AK represents aggregate performance for case period, aggregate performance case period. And of course, this would be Fy measurable, Fk measurable. And then the aggregate reward, team's aggregate reward is given here. It may depend on the common noise Y. And so from now on, I will often omit this Y, right, in related functions. For example, I will often write R, omit the Y in this R, or also some other functions. Let's look at centralized control. So for centralized control, this is the total reward for the team, and this is the total cost for the team. And then, of course, each player will choose control AI, which may depend on the individual noise as well as common noise. And it can be easily shown because of the convexity of C, this supremum is equal to this supremum. This supremum means that everyone uses the same control, and everyone can just use the control that only depend on the common noise. This can be easily shown. So here is some lemma. It's a critical lemma. So it says under some assumption, there exists an optimal solution for this supremum. So optimal solution. And this optimal solution is such that optimal control is positive. And moreover, we have this result. So this is a critical result in term later for establishing the for finding the optimal relative performance criteria. But of course, this condition is rather intuitive, right? It means this is the marginal cost at time k, and this is the marginal reward at time k. So they should be equal at the optimal solution. This is rather intuitive. Let me skip this assumption and the example here. So for the relative performance criteria, definition is similar, but here we need to modify a little bit in the sense that previously in the static models, the relative performance criteria is deterministic. Now here I change it a little bit, and I make it to be stochastic, a little bit stochastic in the sense that it depends on the common noise. Y. So Y here is represent common noise. So it is Y1 up to Y, so it is a pass. And then the rest is the same. And so still we have for example, these three typical examples. So it's similar to the previous ones. The only difference now here is beta may depend on Y, gamma may depend on Y, and this R may depend on Y. This is the only difference. So of course, let me emphasize that in our definition, right, the relative performance criteria capture the relative contribution of a player's total performance instead of the performance at each time period. So which means, for example, if we look at the ratio-based one, right? So this would be the relative performance. In particular, this is total performance of player I, and this is the total performance of the team. And of course, you may also consider, right? We can also consider this type of one. This is path dependent, right? Depend on the performance at each time period, right? At each time period, that's also fine. You can also consider this type of criteria. But here, I think this is less attractive, because if you want to implement the performance criteria, right? If you look at this, then this means that you need to monitoring each player's performance all the time. So this it's here. I just monitor. Finally, I just monitor once at the terminal time. Here, you need to monitor all the time, right? So this is less attractive, and also in fact the result of optimal relative performance criteria of this form is easy to establish. So I'm not going to talk about this kind of form in this talk. Again, suppose, now let's look at the game. So suppose player I use control AI. Of course, could depend on the individual noise and as well as the common noise. And all the other players use control A. Then this player's expected payoff is given here. In particular, this is the original reward. This is the cost, and this is a relative. This is a share he would get based on the relative performance criteria. In particular, this is a realized performance, cumulative performance, and this is distribution of performance of all the players. And then definition of optimal relative performance criteria is the same, right? So we say F is optimal relative performance criteria if there exists an equilibrium A with respect to this F, so that under this equilibrium, each player's payoff is the same as the optimal solution for the centralized control. The definition is the same. And then, so just to recall that the A star is the optimizer for the centralized control problem. And then I defined my beta like this. So essentially, it's the same as the static case. But here, of course, here this I have this. I replace A with this term here. So this is the only difference. It's more general, of course. And of course, this is random. Right? This is random. So so this beta is random, but it is only adapted to Y. Only adapted to Y. It doesn't adapt to any individual noise. And then if beta is defined like this, then my F, the ratio-based one, is the optimal relative performance criterion. So here is an interesting example. So if I think it's interesting because it is deterministic. Because if R is a power function X, is a power in X, and then multiplied by the common noise, right? Common noise here. Then beta is just equal to P. It is deterministic. Similarly, we have an optimal difference-based one. Again, it's similar to the static case. It's just that we replace A with this term here. And similarly, we have a optimal rank-based relative performance criteria, which is based by the optimal ratio-based one and the difference-based one. It's similar. How much time? Okay, almost time. Okay, let me quickly go through the two-layer infield game. Okay, as I mentioned, the top layer we consider a continuum of teams. Bottom layer, each team we have a continuum of players. We can continuum of team members. So first, let's assume we assume a continuum of teams, and first let's consider the control where we assume the control is centralized with each team. First, I make this assumption. So we take a representative team. So this team uses control A, and all the other teams use control A star. Then the payoff for the representative team is given is defined like this here. So this is the original reward. This is original reward for the team, and this, of course, this is the cost for the team. And then the reward is redistributed according to this rule. According to this rule, in particular, this is, I call it the achievement of this representative team. And then this is, of course, the average achievement of all the teams. And then, so you can see that here I introduce the competition between teams from this ratio, And of course, theta capture the competition intensity among teams. And then we say, so of course, we say A star is a team-wise equilibrium if this holds, meaning that if other team use control A star, it's also best for my team use control A star. And we can see, I can show that under certain assumptions there exists a unique team-wise equilibrium. So far it's still one layer problem. It's just top layer problem. Now let's look at the two layer problem. We assume a continuum of teams, and we assume each team has a continuum of team members. We take a representative team and take a representative player from this team. Then I assume the representative member choose control A. I assume all the other members in the representative team use control A prime. And I assume all the members in other teams use control A double prime. Now, let's just focus on ratio-based relative performance criteria. Let's just focus on this. Of course, this is characterized by beta. So from now on, I also call beta the relative performance criteria. Now, suppose the representative team implement relative performance beta. Then the representative member in the representative team, the payoff of this one is given. Is represented by this expectation here. In particular, this is the original reward. This is the cost. Then the original reward is redistributed based on this relative performance criteria within the team. And then this reward is further impacted by the team-wise competition. And then maybe I can skip this. So here I call beta star. Beta is remember beta relative performance criteria, right? So I call beta star A star. So this pair is said to be an equilibrium for the two-layer game. If first of all, beta is an optimal relative performance criteria, given all the members in other teams use control A star. Second, if all the other team members use control A star and my team, the representative team, use relative performance criteria beta star, A star is also equilibrium for my team. So this is a two-layer equilibrium. And the result says there exists a two-layer equilibrium. Moreover, so the two-layer equilibrium here, A star. So this A star is just the unique team-wise equilibrium from the previous result from the team. So this is just the team-wise equilibrium. It's the same one. And then beta, I can compute the beta star like this. It has two terms. The first term, of course, is the one. The first term is the same as the one without team-wise competition, and the second term it comes from the team-wise competition. As you can see, competition increase this beta, beta, and also if we ignore roughly speaking, if we ignore the dependence of this term in theta, then this term will be increasing in theta. This is consistent with intuition. In a competitive industry, larger theta implies it's better to in a competitive industry, it's better to promote competition. So this for the one layer. So for the one layer problem, it can be easily extended to a continuous time setup. Since I'm running out of time, let me just skip it. And I can this can also be easily extended to heterogeneous case for the one layer problem, only for one layer problem. Of course, the heterogeneity lies in the cost function. So different player may have different cost function. And the result looks also similar. So for example, the beta looks like this. And of course, as I mentioned, that so here for the heterogeneous case, I don't put any weight. But if you want to put some weight, say you can also consider the heterogeneous case with some weight. For example, you can put more weight for those players with larger cost function, meaning that you care more about the disadvantaged players, right? So you can also define relative performance criteria with respect to this weighted function. But here is a subtle thing. Here is for the team's benefit, right? For the team's benefit, we consider the weighted function. But for each individual doesn't care about the weighted function. So then optimal relative performance criteria with respect to W is if it is optimal, then it means that there exists an equilibrium such that A star is optimal for this, such that this equilibrium is also an optimal solution for the centralized control. But if we decide to look at put some weighted function which is not identically equal to 1, then we have a negative answer, which says optimal relative performance criteria with respect to W may not exist. And we have this. We have an example. We have an example, and a one-period example showing indeed showing that optimal relative performance criteria with respect to W does not exist among all the relative performance criteria, not just restricted to these three types I focused on. So because of time, that's all of my talk. Thank you for your attention.
Thank you, Dr. Zhou, for the interesting talk. So, any questions or comments from the audience? Yeah, perhaps I would like to ask one first, because I think I have missed something quite important at the very beginning. So when you say about the optimal relative performance criterion, so how do you define the so-called optimality here? So because to me, this criterion is related to how we distribute the reward. So this optimal is for one player or the whole team, or so how?
That doesn't matter here, because if it is optimal for each player, then it is also optimal for the whole team. The vice versa. It doesn't matter. And here, what I defined it is like this. Let me just go back to the. To this one. Say so each player, right? Because for example, consider a homogeneous case. In a homogeneous case, then the team's reward is the same as the individual's reward, because you have if you average out, you take the average, it's the same one. Then suppose I have a relative performance criteria which may not be optimal. Okay, which may not be optimal. Then let's take a performance criteria F. Take a relative performance criteria F. So I look at this payoff function for each player. This is for each player, right? For each player. Then of course, for each player, and then I can define game. There is a game, right?
Yes.
The game, and then I look for Nash equilibrium, which means if other player use control A hat, then it is also optimal for me to use A hat, and then I call A hat a Nash equilibrium, right? Then of course, then you plug this back into this expression. So this becomes A hat, this becomes A hat, right? This becomes A hat, this becomes A hat. So this function, of course, if you can see that, of course, I change it to A. This function, of course, if you write it out, it's just R minus C here. Of course, it will not. In general, it will be smaller, no bigger than the value V. V, what is V? V is the optimum value for this one. V is the optimum value for this one, right? So in general, it will be smaller. But here, optimal one means that if I carefully choose this F, this will be equal. Then I call this optimal.
I see.
Yes.
It's
So
some
it is
sort of
optimal for each.
achievable.
Yes. So it is optimal for each individual. But if it is optimal for each individual, it is also optimal for the whole team, and also vice versa. Yeah.
I see. Okay. So another question may be quite naive, because when I see your work, so you are dealing with the continuum of the payers. Of course, that will be related to the mean field game setup. But do you think it's possible to derive sort of convergence or error bounds between the continuum payers and the maybe discrete number of payers?
Oh yes, definitely, sure, yes. Of course, in terms of a convergent rate, these kind of stuff, it depends on how I haven't tried, but intuitively, at least intuitively for the convergence, yes, indeed, it should look like this. It should have this convergence. Otherwise, the model is not good.
Yeah, correct.
I expect there will be convergence. But of course, I didn't prove it. But I expect that there should be convergence. And as for how technical the convergence will be, the proof for the convergence will be, at least I think for the one layer problem, not a big issue. For 2 layer, I don't know how difficult it would be.
I see. Thank you. So let me make a last call for the question. Yeah, Dr. Zhou Zhou.
Yeah.
Okay.
Yeah.
Please
Thank you for the talk. So here you consider a discrete time model.
Yeah.
So why you do not consider a continuous time model? Because there is some technical issue. So
for the one layer problem, the continuous time model is not an issue. As I mentioned, I can easily generalize to continuous time model. And for the 2 layer problem, there are some reasons. One reason is that because here I consider path dependent. I mean, you can see that this is not a Markovian. Everything is path dependent. So if I work on continuous time, I need to work on path. If I would like to work on path dependent, this would be might be an issue and might be technical. This is one reason. Another reason is for this convergence. I'm not saying it's not possible, because it's just another reason is for the team-wise equilibrium. Where is it? Another reason is for the team-wise equilibrium. So here, it's like a it's like a, so here it's the proof, right? Our proof relies on so first the proof idea is we prove the convergence of or stability of the optimal control. Then use the fixed point argument. So when I prove the stability, right, I use the backward induction because I have finite time horizon, finite time periods. So this technique doesn't work for continuous time case. But of course, for continuous time case, if you consider Markovian setup, you can use PD, which then it is still possible. I just didn't try it, but it's still possible. Yeah. Depend on how difficult, depend on the model, how difficult or what kind of condition you put. But it's still possible. Yeah.
Okay, thank you. So another question is that you said it's better to promote the competition, but this is when the agents are all homogeneous, or they can also be heterogeneous.
Oh, here this result only for homogeneous case. For heterogeneous case, so of course, intuitive, I guess we would get the similar result, but I don't know. But intuitively, I would expect that. But on the other hand, I didn't prove the heterogeneous case because for heterogeneous case, there are some technical issue. For the 2 layer problem, there are some technical issue.
Yeah, because from some paper that I saw, when the agents are heterogeneous, the conclusion can be different.
I see. Yeah, I don't know.
Okay. Thank you.
Thank you. So any other questions from the audience? So if no, let's thank our speaker, Dr. Zhou, again. So thank you. Thank you very much.
Thank you.
Thank you for the interesting talk here. Thank you. So thank you all the participants of this session. I would like to call this the end of this session. Thank you very much. Thank you very much.
Thank you, Patrick. Thank you.
Thank you.
Thank you.
Thank you, Charles.
See you soon.